A viewer recently asked a really good question on my proportional control line follower video. They wanted to set base power to 70, but no matter what KP value they tried, the robot kept going off the line. This is a great question because it shows one of the limitations of using only proportional control at higher speeds. And this is a very real robotics problem, because once we make the robot go faster, we can't always fix the problem by just increasing the proportional gain. In this video, I'll show you one simple change that can make the robot much more stable at higher speeds. The basic idea is simple. The robot can go fast on easier sections of the line, but when it needs to make a bigger correction, it should slow down. Kind of like how you would drive a car. You might go fast on a straight road, but when a curve comes up, you slow down so you can stay in control. This is the program from my previous proportional control line follower video. If you haven't watched that video yet, I recommend watching it first because it forms the foundation for what we're doing here. In that program, we used a fixed base power of 30 and a proportional gain, or KP of 0.3. Inside the loop, we read the deviation from the quad RGB sensor. Then we calculate the motor powers using the proportional correction. The farther the robot is from the center of the line, the larger the correction becomes. At lower speeds, this works pretty well. But what happens if we simply change base power from 30 to 70? Let's try it. As you can see, the robot is definitely moving faster, but it does not correct quickly enough. It starts to drift away from the line, and eventually it completely loses the track. So our first thought might be, okay, if the robot is not correcting enough, let's change KP. Before I show you what happens, take a second to think about this. If we want a larger correction, should we increase KP or decrease KP? The answer is we should increase KP. A larger KP means the same deviation will produce a larger correction. So now let's increase KP from 0.3 to 0.4 and see what happens. This is better in one way. The robot is now correcting more aggressively, but now we have a different problem. The robot starts oscillating around the line. It turns too hard in one direction, then too hard in the other direction, and this back and forth motion becomes unstable. If we let it run long enough, it can still go off the line. So this tells us something important. At higher speeds, simply increasing KP is not always enough. Actually, increasing KP too much can make the robot unstable. By the way, if this video is helping you so far, please hit the like button. It really helps support the channel. And subscribe to tune in to future videos. Now, let's think about this as if we were driving a car. Imagine you're driving at 70 miles per hour and there is a curve coming up. Would you just keep the exact same speed and try to steer faster? Probably not. You would slow down during the curve so you have better control. That same idea applies to our line follower. Instead of forcing the robot to use a fixed base power of 70 all the time, we can let the robot use a maximum base power of 70. But when the robot needs a larger correction, we reduce the base power. So the robot goes faster when the line is easier to follow and slows down when the line becomes harder to follow. I'll also upload the full program for this project as a learning pack on the new Learn As You Explore hub. You can find it at hub.learnasuexplore.com. Link is in the description and pinned comment. Here is the updated program. The main idea is that instead of using a fixed base power, we will calculate a dynamic base power. That means the base power can change while the robot is running. At the top, we define a helper function called clamp. This function keeps a value inside a specific range. If the value is too low, it returns the minimum. If the value is too high, it returns the maximum. Otherwise, it just returns the original value. We'll use this because we do not want our motor power values to go outside our defined range. Inside the button B function, we now define two base power values. We define max base power as 70 and min base power as 40. This means the robot is allowed to go as high as 70, but during larger corrections, it can slow down to 40. So we are not saying the robot should always drive at 70. We are saying 70 is the maximum base power. Then we define KP as 0.35 and slowdown as 1.75. The Kp value is still our proportional gain. It controls how strongly the robot corrects based on the deviation. I bumped this slightly from 0.3 to 0.35. The new variable is slowdown. This controls how much the robot slows down when the correction gets larger. A higher slowdown value creates a stronger braking effect. A lower slowdown value creates a weaker braking effect. These numbers are not magic values that work on every mBot2. You may need to tune them for your own robot, your own lighting, your own floor, and your own line following map. I found these values by testing a few different combinations on my robot. Inside the loop, the first step is the same as before. We get the deviation from the quad RGB sensor. Then we calculate the correction. The correction is Kp times deviation. This is the same proportional control idea from the previous video. If the deviation is small, the correction is small. If the deviation is large, the correction is large. Now comes the important new part. We calculate dynamic base power as max base power minus slowdown times the absolute value of the correction. This line says, start with the maximum base power, then reduce it based on how much correction the robot needs. We use the absolute value of correction because we do not care whether the robot is correcting left or right. A large correction in either direction means the robot should slow down. So if the correction is small, the robot stays closer to the max speed. If the correction is large, the robot slows down. But after calculating this dynamic base power, there is a chance the value becomes too low or too high. So we clamp it. We keep the dynamic base power between the minimum base power and the maximum base power. In this example, that means the dynamic base power will always stay between 40 and 70. So no matter what the correction value is, the robot's base power stays inside the range we selected. Next, we calculate the left and right motor powers. This is almost the same as the original program. The only difference is that we replaced the fixed base power with dynamic base power. So now the robot can automatically slow down when the correction is large. Then we clamp the left and right power values. This part is important. We are not clamping the motor powers between min base power and max base power. That would be wrong. The individual motor powers may need to be positive or negative depending on the direction of the turn. So we clamp them between negative max power and positive max power. In this case, that means between negative 70 and positive 70. Finally, we send those values to the motors. And when button A is pressed, we stop the motors. Now let's try the updated program. This is much better. The robot is still moving faster than the original base power 30 version. But now, when it gets into a harder section of the line, it slows down instead of blindly forcing itself to stay at power 70. That gives it more time to correct. You can still see some oscillation, especially after curves. That is normal at higher speeds. In a future video, we will look into improving the oscillations. But even with this one change, the robot is much more stable. It does not veer off the line like it did when we used fixed base power 70. So the big takeaway is this. If your line follower fails at high speed, do not assume there is one perfect Kp value that will fix everything. At some point, the robot is simply moving too fast for the curve. So instead of using one fixed base power everywhere, we can use dynamic base power. The robot goes faster when the correction is small and slows down when the correction is large. That gives us a simple, practical way to make the robot faster without making it completely unstable. I'll upload the full code for this project to the new Learn As You Explore hub at hub.learnasuexplore.com. I'll make a separate video later where I walk through the hub and the different sections. Just know that you can grab the full program from there. Try it on your own mBot2 and tune the values of Kp, slowdown, min base power, and max base power. If you found this helpful, please like the video and subscribe to Learn As You Explore. And if you have questions, or if you try this on your own robot, leave a comment below. I'll see you in the next one.